Chapter 5. 5-1. Okay. We are, there we are. I'm too big. Here we go. 5-1. Now we're on the screen. Okay. We are going to examine the normal probability distribution. Okay, the normal probability distribution has 5 characteristics we're going to talk about. First of all, it's normal when your mean, we didn't call it normal before, we called it the symmetrical or bell-shaped distribution. But you get the normal distribution when the mean, median, and mode are all approximately the same, are all approximately equal. They don't have to be right on the dime the same number, they just got to be really close to each other. This is a symmetrical, bell-shaped distribution. Oh, symmetrical and bell-shaped. We're going to draw it in a minute. The area under the curve equals 1. That's because our probabilities are going to match the area. And then the curve approaches but never touches. The x-axis. So what does it look like? It looks like this. Here's our x-axis. Okay, at the top of the curve, looks like this. There's the top of the curve. Then what happens, that has concave, it has that direction there, it's called concave down. It's like a cereal bowl upside down. See that curve going, see why they would call that concave down? Yeah. Now at this point, the concavity switches. Concavity switches ever so slightly, now it becomes concave up. See how that changed a little bit? See how now it's like your cereal bowl, it's the right side of your cereal bowl? Same thing over here, the concavity switches. That's what happens when you don't brush your teeth. Very good. So where that point where the concavity switched is called an inflection point. Inflection. So at the top of the bell curve is where our mean, median, and mode would be, and we just go with the mean. And our symbol, mu. It's supposed to look like a U. Mu.
Wait, that's supposed to be a U? I thought it was supposed to look like an M. I know, I've been like drawing...
No, it's a U.
I've been drawing a fancy M for
Wait, how is everybody seeing M?
I don't know.
I don't see M at all.
It's U.
I see...
It's a U with like 2 little monkey tails on it. It's a Greek letter though, but it's a, I would call a U.
I don't see the M. I see golden white.
I've been drawing a
Oh, I think they see like a capital M, like this kind of M you're talking? Like an M.
That's what I've been drawing this whole
That's the M that they see, a big M.
That's what I've been drawing for weeks.
Oh, it's a U.
That's why I got those wrong on my teeth.
Oh,
I figured
yeah, the shape of the letter.
It's easier to remember because M means,
Yep.
you know, that whole thing.
I don't know what to tell you. Wasn't Greek. I don't know where they came up with their alphabet. Okay, this distance over to this inflection point.
You're not funny in that case.
I am.
Shut up.
Quiet. This distance is equal to your standard deviation. I know. Well, that distance over to the inflection point is your standard deviation. All right.
Is the two inflection points
Yep, this would be a standard deviation distance also, just to the left.
No, I mean, like,
Oh.
them together, is it the square? Is the variance?
No.
It's not, oh.
No, because you'd have to square that number to get the variance, not double it. Yeah, we are. Not today. Okay. So, what does standard deviation tell us about a data set? What does that indicate? How spread out the data are. Okay, so knowing that, our first example. I'm going to give you 3 symmetrical graphs. Here's one, yep. Here's a real tall, skinny one. Here is a shorter, fatter one. And stacked there, and then this one is going to be, oh, I'll make it skinnier yet.
What do you do in shorts?
We'll see. So I've got 3 graphs here. We'll call them A, B, and C. Okay.
OCD is off the charts right now.
That's all right. A, B, and C are there. $45 and $60. Okay, we're going to make a little table of answers. A, B, C. I want you to tell me the mean of each graph, and then I want you to order the standard deviations from smallest to biggest. So the standard deviations from smallest to biggest. We won't be able to tell what the standard deviations are, but we're going to be able to tell which one has the smallest standard deviation to which one has the biggest standard deviation. But you will be able to tell me the mean for each of the 3 graphs.
A is 60.
A has a mean of 60.
Then 45, 45.
And then 45, 45. Any questions there? Because the mean is right on the line of symmetry. You're good there?
Yes.
Okay. Which one has the smallest standard deviation? Why A?
That part, that outwards part.
Yep, it's the skinniest. It's how wide it's not how tall, it's how wide it is. You can see I tried to make A the skinniest graph. Everything's compact in here. So A has the smallest. Which one has the biggest standard deviation? I would say C, because C is spread out more. See how wide it gets here? See how fat the graph is getting here?
Wait, that's C?
C. C is the widest. So this one, C would have the biggest standard deviation.
Oh.
And then B I tried to get in the middle. It's a little bit wider than A, but skinnier than C. So this would be the middle. So it's all in how wide the graphs are. That's what your standard deviation is telling you. The wider the graph, the bigger the standard deviation.
So
Not how tall.
what exactly are we looking at when we're, are we looking
At the big body of the graph, where all the, like this, the main part of it.
when you
Because these do go out forever. All of them go out forever. They
yeah,
keep.
'cause that's what I'm looking at. I'm looking
Don't look at the bottom part. No, look at the big part, how wide it is. Because they all go on forever. I could put arrows on these. They're all just going to get closer and closer and closer to the x-axis and go out to infinity.
Okay, is the height anything?
Nope, that's how many data. The tallest means I had more data in that set. So they're exactly. The height is just an indication of how many data points you had. Good? So we got understanding that. All right, so I don't want to lose anybody. Okay. All right. It was supposed to be done like this morning, and it's also supposed to be melted by this afternoon. Yeah, it was supposed to start last night, so it's a little, probably by the time we end school, it's going to stop and start melting.
Thank God.
Just get me out of here.
Yeah, thank you.
Thank you.
Yeah.
The empirical rule. This is what we're going to spin off on in this chapter. The empirical rule is a good way to approximate
No, we did this one before, didn't we?
Yep, the area under the curve, under the normal curve.
I was going to say it down.
When I throw these numbers out, you're going to say, oh yeah, it was the 68,
Oh, yeah.
95, 99.7 rule.
No, I knew what it was. The title. I felt smart for a while.
Okay, so we're going to review that empirical rule. Make this graph a little bit large so we can put our numbers in it. It is a nice normal curve. And I didn't talk about that inflection before, the inflection point, and I don't really care that you, I like to just go and draw it this way. You just need that normal curve.
Are we just drawing on that, or is it?
Nope, we're just going to draw, well, yeah, I'll just draw in here.
I cannot draw it normal.
I can't do a very good job with them either, but.
Schwartz, yours is a lot better than ours.
Here's our mean.
I actually had a pretty good one.
And then remember, it was 3 standard deviations out to the right, and that third one kind of took you to where it was tailing off. So just kind of estimate 3 equally spaced chunks here. I'm going to do the same thing on the other side. I didn't do a very good job making them equal.
Everyone has those days, Schwartz.
I know. And each of those are 1 standard deviation apart. So this one is the mean plus 1 standard deviation, mean plus 2 standard deviations, and mean plus 3 standard deviations. And then the backwards.
Why are we doing this again?
Like I told you, today was all review. Because you don't remember all of it that you need.
But it's in our notes already.
Well, then you're good to go, aren't you?
But I had to write these ones down.
Yes, you do.
I don't understand these.
I know.
Where you put the means in and keep putting it in.
That's not my problem either. You people got to tell me things I can fix, not things I can't fix.
Wait.
Oh boy.
Because everybody doesn't want to be here.
I know. People are on vacation and we're stuck here. Nice.
And it's in why everything.
Today's my last day.
Well, there we go. Hang in there. Okay, our percentages. Remember the 68 was if you're within 1 standard deviation of the mean. That means these 2 chunks. Stay with me.
I'm staying with you.
Those 2 chunks contain 68% of your data set. And because it's symmetrical, that means each side is 34%. The 95 meant if I went from the mean and go out 2 standard deviations, that would be these 4 pieces here. Those 4 pieces would contain 95% of your data. So those 4 pieces contain 95%. And we did the math already. 95 subtract 68 divided evenly, we had 13.5% in each of these little slivers. And then our last chunk, if I go out 3 standard deviations, that will contain 99.7% of your data. Well, it's there, because the graph goes on forever. It's that 0.3% that's spread out. So there's not much data out there, but there is a tiny, tiny bit of it.
So it goes on forever.
Goes on forever. And then this, each of these, if you do the math, is 0.0235. 2.35%. And then again, it's that 0.3%. You get 0.0015 in each of the tail pieces. Nope, it can't. We're almost there, though. I have 2 examples left.
And that's it?
And that's it.
Elbow cord?
And then number 2. Wasn't listening. I didn't hear. I was focused on my next example.
How much room is this going to take?
It's a little picture.
You know, I'm just going to try to fit it in.
Approximate the mean and standard deviation for this graph. Normal distribution, 2.9 and 4.1. And that's all I'm giving you. Yes, you can.
Divide by 2.
Okay, so she said we're going to assume that these are symmetrical, so she said to get the mean, we're going to average those 2 endpoints, and she is correct. So to get the mean,
3.5.
she said add them up and divide them by 2. And what'd you get, 3.5?
Yep.
Okay, so the mean is about 3.5. That would be a good approximate. How do I figure out the standard deviation? What assumption do we have to make here? That there's 3 equal parts on each side. Like this would be the 3rd standard deviation out. That would be a good assumption because it's about where it starts to tail off. So you're going to assume that this 4.1 is the 3rd standard deviation. So what you want to do is take this distance and divide it into 3 equal chunks. Does that make sense?
Yes.
So how do I get this distance? We're going to subtract. So 4.1 minus 3.5, what's that distance? 0.6. And then we're going to divide by 3. That will give us a distance of 0.2. So
Good job, Aunt Casey.
that will be our standard deviation. Because if I now add 0.2 and 0.2 and 0.2, this would be 3.7.
So why do you have to subtract them?
Because I need the distance. I need this distance because I'm going from here to here, from here to here. I need 3 equal parts. So to get a distance on a number line, I subtract.
So what does variance show then?
That's another indication of how spread out things are. The bigger the variance, the more spread out. Standard deviation and variance do the same thing, just that one has units squared and one doesn't. But they both do the same thing.
So variance is more like for bigger graphs?
No. I think variance is just used in different formulas that we're not familiar with, but both of them do the same thing. They tell you how spread out things are.
See, that's why I
No, they are essentially telling you the same information. All right, last one. Off of the empirical rule.
Wait, last one total?
Total.
No.
Told you there wasn't much today. I mean, we chit-chatted for half the hour and we only got 15 minutes notes here. I don't want to cover a whole lot before spring break. I'm going to forget most of it, but
You're smart, you know that.
so I'm kind of dragging my feet here and only doing a little bit. Okay, IQ scores. Are normally distributed. With an average of 100 and standard deviation 15.
What does it go to?
I don't know what the IQ scale is. I feel like it's like 170, 180.
I feel like IQs are
Well, for some people they are.
It could be in
Like Einstein.
I mean, I don't know. I think I don't know.
But there's like no just like one set. Like
No, no. But those super brilliant people do tend to have IQ scores off the charts. They're in this part of the graph up here.
I want to be in that.
Yeah. Well, we'll get it. I want you to make the graph so we can see the divisions, and then I'm going to ask you some probability questions. So, let's make the graph. It is normal.
Are we ever gonna need a y-axis for this?
Nope.
Cool.
Oh, the middle is 100,
The middle is 100,
and then you add 15.
and then you keep adding 15s 3 times.
Yep, and then you minus 15.
There it is, and then I'm going to ask you some probability questions. This part's easy. You can't tell me anything in here. I could even question and make these hard. There's no way. So if you add 15s, 115, 130, 145. See, anybody above a 145, you're up in that beyond genius category.
How do we get there?
I don't know. I think God put you there. I don't think you can get there all on your own.
Jesus.
Yep. Now we subtract 15. Not that I can subtract very. 85, 70, and 55.
Oh my gosh, I did that all in my head.
All in your head.
Good job.
So,
Impressive.
You're on your way to that category.
That was actually really well played.
select a person at random.
Let's let me. Let Austin.
We use Austin as an example.
Yes. I'm ready to be a guinea pig.
What is the probability that your person has an IQ score between 70
No, just get it off.
and 115?
Slaughtered the word random.
What? How do you slaughter the word random?
My pencil was moving faster than my brain.
Slaughtered the word.
Okay, so we're going to use our graph and our probabilities that we had on there to answer this question.
Sorry.
What?
Like eight, we're gonna do eight.
Yeah, we'll do 2. I'm just going to do 2.
Can we do like less than or equal to?
Yeah, you can say equal to. It's not going to make a difference because these are approximates. This empirical rule, these are approximate values. And what's going to happen as we move through this chapter, I'm going to be able to say something like, what's the probability they have an IQ score of 90 to 112? You know, things that aren't on these dividers. That's where we're headed.
Say what that is again?
Okay, so between 70 and 115, that's this chunk of the graph, this chunk, and this. I need these 3 chunks added together is all. So if you go back to your notes, what 3 pieces are those?
68.
It's the 2 34s and the 13 and a half. I just have to add those 3 pieces up.
81.5.
Wait, that's 13 and a half? I thought that was point
There's
thirty
no
one
way it's
three five.
oh yeah.
Yeah, that's 13.5%. That's the decimal, 0.135.
Okay.
So you can talk percents or you can talk decimals. They're the same thing. Just be consistent.
Yeah, 81.
So 0.135 plus the 0.34 plus the 0.34. If you want to do 68 plus the 0.135, whatever it takes. You're just adding chunks of your graph together. And what does that come out?
Not getting me out of it.
What is it? 8 what?
81.5.
80, so 0.815?
Yes.
Okay, last one then. What's the probability your person has an IQ score less than 70? Eesh. Is that a good probability?
Find the 70 mark.
No, but
It's not likely that that's going to, by picking one person at random from the population,
still people there.
there are still people there.
Isn't that literally like 2%?
It's very small. It's what's 2 chunks of the graph? It's these last 2 chunks, the tail piece and the first chunk. So if you look, your tail piece, 0.0015, and the first chunk is 0.0235. So not likely that to have this happen.
So you have the same chance as being super smart that you do being super dumb.
Very good. Very good.
Wow. I bet
Yes.
I'm super smart.
Hey, are
Yes.
Yeah,
Are
me
these
too.
examples kind
kind of accurate?
This is absolutely accurate data, yes.
Okay.
Not all the time, but
So this is like
Okay, well,
2.5
this
then?
confuses me then, because then I'm gonna like tell someone something and.
no, this is real. The average IQ score is 100 with that, yes. It hasn't changed over time.
On this is an IQ test right now.
Okay, that's all I have for you.
Wait, can we get a calculation?
Can we get a calculation?
Point
Can I get a calculation?
Oh,
50?
2.5.
2.5. 2.5%
Well, we gotta
chance.
add the zero though, because,
4, 5, he's right. That is. Because the 5s make a 0.
Smarter than I
I don't
look.
know.
3 and 1, 5,
I'm just saying,
2.
'cause-
What?
What's it called?
What?
With the. Yeah, yeah.
Oh, you want me to put a 0 there? You want me to write the 0 down? I see what you're saying. There, are you happy now? Everybody in their happy place?
Yeah, yeah.
Free IQ test fast, free and accurate online IQ test. Let's do that.
Let's see, we've got Wednesday in stats, page 198.
Ow!
I move to
Can you, like,
male
change
gender.
the question?
You know what, I'm gonna do you a huge favor.
God, please.
Let's do this assignment, well, Kelly's gonna need it, in class tomorrow, and we'll check notebooks tomorrow. That'll be our hour tomorrow. How does that sound?
Awesome.
So I'll write it down for, is anybody gone tomorrow? So if you're gone tomorrow, you gotta write it down and do it. 2.
Okay, when's this due?
So you can, this will be due, Monday when we come back. Because I'm not gonna check it Friday, because there won't be anybody here.
What day is it today? It's Wednesday?
Wednesday?
You're not doing that. Is that it?
I'll have your tests to go over tomorrow.
You really staffing them on?
Yeah, so, let's not complain, it's not a homework assignment.
Okay, okay.
So we've got, still got 20 minutes to just
Chill.
chill.
But
So-
of course, you're taking my notebook.
Yes, I am.
Huh. So I'm gonna have to.
Photocopy it,
Alright.
take them with you.
So how many people are we actually gonna have here Friday?
Like 7.
Everyone raise your hand if you're gonna be here Friday.